Ever notice how radiation in movies turns people into superheroes? A bite, a blast, boom, superpowers. Last week, I had a PET scan and couldn't help but wonder, where's my radioactive upgrade? Movie magic aside, radiation plays a real-life starring role in saving lives and advancing science. Let's uncover how. This is Real Chem. Imagine discovering something invisible, powerful, something that seemed to defy the rules of nature. In 1896, Henry Becquerel did just that when he found uranium could emit energy on its own. Soon after, Marie and Pierre Curie identified more elements with this strange behavior, polonium and radium, and named the phenomenon radioactivity. But what was this mysterious energy? In 1899, Ernest Rutherford looked closer, revealing differences in these mysterious emissions. He discovered alpha particles, positively charged and easily stopped. Beta particles, negatively charged, more penetrating. Gamma rays, neutral, powerful and able to pass through most materials. Let's explore how these and other nuclear processes work and how to write equations to describe them, just like we do with chemical reactions. Alpha particles are essentially helium nuclei, 2 protons and 2 neutrons bound together. When an atom undergoes alpha decay, it emits one of these particles. In nuclear notation, helium is written in this fashion. The bottom number 2 represents a charge from 2 protons. The top number 4 represents the total mass, 2 protons plus 2 neutrons. In nuclear reactions, we often use the Greek symbol for an alpha particle. Let's look at the balanced nuclear equation for the emission of an alpha particle from americium-241. A real-life example of americium-241 alpha decay is its use in smoke detectors. In nuclear equations, both mass, the top numbers, and a charge, the bottom numbers, must be equal on both sides. How about beta radiation? Beta particles are simply electrons, emitted from the nucleus during beta decay. Since an electron's mass is very small compared to protons and neutrons, we approximate it as 0 when balancing nuclear reactions. However, we do need to account for its -1 charge. Again, in its decay equation, both mass and charge remain balanced. An example of beta emission is that from iodine-131, which is commonly used to treat thyroid disorders such as hyperthyroidism and thyroid cancer. Let's move on to gamma radiation. Gamma rays are high-energy photons, packets of light with 0 mass, 0 charge, but plenty of energy. Unlike alpha or beta decay, gamma emission doesn't change an atom's atomic or mass number. Instead, it helps the nucleus shed excess energy, moving to a lower energy state. This is key to technetium-99m, one of the most widely used isotopes in medical imaging, including cardiology, oncology, and neurology. The M stands for metastable, an excited nuclear state that lasts longer than usual. When technetium-99m decays, it releases energy without altering its atomic number or mass. So far, we've covered familiar particles, helium nuclei, electrons, and photons, but positron emission introduces something new, antimatter. Some nuclei emit positrons, the antimatter counterpart of electrons. Positrons have the same mass as electrons, but a +1 charge, so we use the symbol beta plus to represent them. For example, fluorine-18 undergoes positron emission, following the same mass and charge balance rules. Positron emission tomography, or PET scans, take advantage of a sci-fi-like phenomenon. When matter and antimatter meet, they annihilate, releasing energy. When a positron collides with an electron, they produce a gamma ray. PET scanners detect these gamma rays to create images of metabolic activity, helping doctors diagnose conditions like cancer and heart disease. Chemistry often revolves around electrons, but sometimes it's all about the nucleus. While nuclear reactions share some similarities with chemical reactions, they follow their own distinct rules. From smoke detectors that protect us to medical technologies that diagnose and treat disease, nuclear processes have a powerful impact on our lives. Getting bitten by a radioactive spider might sound cool, but in reality, the real superheroes don't wear capes. They wear lab coats.